All right, recording's on, November 2nd, second half. So we were talking before the break about this proposition that says that we can compute the number of spanning trees tau of g via an induction that uses mainly this recursive step as its main inductive step. So let's just write this down. I think it's relatively clear from having done it in an example, but let's write down the proof. So maybe I'll take this over the next page just so we can write it. Make that a little larger. So why is it that we can use this to compute tau g recursively? Well, the point is really just, why is this last step true? I guess that's not obvious. Right? I think if we believe, having done the example, I think we understand why all these rules work. And if we believe that D is true, then we can see that we have a recursive algorithm. We believe A, B, C, and D hold, then it's easy to see how the algorithm works in the induction. And as we said, A, B, and C, these were properties that we already agreed upon, that the number of spanning trees in the graph satisfy. So properties A, B, and C don't really require any further proof. But for D, it's pretty interesting. And it's kind of an idea that gets used a lot when you're working with spanning trees. So why is it that tau of G should be tau of G delete E plus tau of G contract on E? And this is really one of our counting principles at work. What we're going to use is, in fact, the combination of two of the counting principles that we've sort of seen show up before. We do a sum principle where we take tau of G is the number of spanning trees T in G, okay? And we take this set and we break it up into two disjoint pieces that are going to have this size and this size, okay? That would be using sum principle. So the claim is this is equal to the number of such T that avoid using the edge E, such T that have, that avoid E. In other words, E is not in T, plus the number of such spanning trees that use edge E. And again, assuming E is a non-loop edge. Okay, I mean, it's hard to argue with that you take these spanning trees and, well, either they use E or they don't. So this number should be the sum of these two numbers, because we're breaking up the set into a disjoint union. And this, the spanning trees that avoid using E, it's not too hard to convince yourself, oh yeah, those are the spanning trees that are in G delete E, G minus E. So again, let me remind you what the picture looks like. You got your graph G, the edges V and V prime, here's the edge E, and then, you know, there's the rest of the graph down here doing all sorts of crazy things. And the point is, if you've got a spanning tree, maybe I'll draw this down here. A spanning tree, let me draw it in red, that manages to somehow avoid using that edge E, then okay, that's the same thing as just a spanning tree in G without the E, with E deleted. Maybe I'll just do this. Again, I seem to keep forgetting that I have the capability to copy and delete things. So let's take that. Wow, didn't mean to do that. Let me move this over here. Will I be able to grab it? Yes, I grabbed it. Okay. All right. So that red tree, T, I can't seem to grab the thing. If it was in here and it managed not to use the edge E, it's the same thing as a spanning tree in the deletion. So you have to convince yourself of that there's this bijection between this thing is, we claim, tau of G minus E. Okay, and minus was a bad, I really wanted to do the backslash E. There we go. On the other hand, this one I'm claiming is the same as tau of G where we contract on E. And so let's think about that. Again, let me draw a picture. Maybe I will, oh yeah, this previous picture had a certain deficiency. It looked like it never got to the edge V prime. So let me do that. All right. Let me now draw a picture of one that uses the edge E from V to V prime. So we've got a rest of our graph, looks like some crazy thing, who knows, blah, blah, blah. I suppose I've got a spanning tree that's using this, and maybe it's got some stuff over here, who knows, it's going all the way around like this, and maybe some things there. But then the point is that you can get a bijection. Let me write this carefully. There's a bijection between that set, whose cardinality we're taking, and the spanning trees of G contracted on E. And so let me draw, roughly speaking, how that works. So here's a picture of a spanning tree in G that used the edge E right there. Well, all I do to get one that doesn't, or excuse me, a spanning tree that is in the contraction is I contract it down. So here's my contracted graph, which again has this, all these other things going on in here. And that same spanning tree, I just draw the rest of the edges that it had as they were before, just like in the picture above. And the point is, this edge right here, the E, it got contracted down. I won't make the disgusting noise, but imagine doing the same thing in the tree T and squeezing it down. You get a spanning tree in the contraction. And this fact requires some thinking. I claim that you really should, this is not 100% obvious. You need to think a little bit about why this is really a bijection. And what you should really think about while you're doing that is, why did we have to assume that E was a non-loop edge? This would have been wrong. Well, we didn't even define what contraction was when it was a non-loop edge. But I guess that's not so much the main issue here. The main issue here is thinking about, why do you actually get a bijection here? And one thing you should think about is the backward map, right? If I start with a spanning tree in the contraction, that's what this was supposed to be a picture of, by the way. This was my G, this was my G delete E, this is my G, and this is my G contract on E. And those red things, like this was a T that didn't use E, and this is t with e, well, t still didn't use e, so it's the same t. In this one, it's a t that did use e. What I'm saying is you take t and you contract on the e. But going backwards, if you start with your spanning tree here, you should think about uncontracting on the e to get the spanning tree there. And you should really think about why it is that if this was a spanning tree, this one will be a spanning tree. And if this one is a spanning tree, why is this one a spanning tree? Okay, so there's a little bit of thinking to do. But if we believe that, then this thing, this set has size tau of g contract on e. Okay, so what we've convinced ourselves is that tau of g is equal to tau g delete e plus tau of g contract on e. Everybody okay? Questions about how that goes? All right, I will be so bold as to say end of proof there. Good. So we have one algorithm for computing the number of spanning trees. It's fine for your homework, but let's get a better method for computing the spanning trees, one that's much more interesting and useful. And we'll use that first one to derive why the second one works. Okay, so this second method, it actually involves linear algebra and matrices. So this is going to be one of the times in our class where we have to remember how matrices work. We already in our exam used determinants a little bit. We're going to use them again. So I have to introduce a matrix. I don't know why I wrote out definition as opposed to saying defin, as I usually do. So we're given our graph G, vertices and edges. And now it's not even going to matter whether it has the loops or the not. Multiple edges are fine. The loops will be irrelevant. You'll see. So we may as well assume that they're not there. So remove them. Okay, I'm going to define this matrix called its Laplacian matrix, after Laplace. Where do I put that over here? Laplacian matrix. Laplacian matrix. And actually, I wanted to say the size of this matrix is going to be square. It's going to be the number of vertices by the number of vertices square. And okay, so it has rows and columns that are indexed by the vertices. Capital V. And the entry that's in the little V prime location, where you have V and V prime are two vertices, depends upon whether you're on the diagonal or not. Okay, so let me say it like this. L of G, sorry, Laplacian matrix is going to be called capital L of G. This is a little messy. Let's make that better. L of G, V prime. So by this, I just mean the V prime entry. The matrix. And what it is if you're on the diagonal, so if V is equal to V prime, just the number, it's the valence of V. It's the degree within G of V. Okay, so it's got the vertex degrees going down the diagonal. And when you're in the off diagonal, V is not equal to V prime. So you've got V over here, you got V prime there. You just count how many multiple edges there are between them, and you take the negative of that number minus the number of edges, E and E, from V to V prime. Okay, well, seems like a crazy thing to do, but let me show you an example. Not clear how we're going to use this yet. if G was our example from before, but I'm going to take away its loop, right? So we had 3 vertices here. I don't know if I'm labeling the vertices in the same way. I seem to keep changing the labeling of the vertices, but I think I'm labeling the edges in the same way. It's got those edges. Then this thing has a Laplacian matrix that is 3 by 3. It's rows and it's columns. I'm just putting the labeling of the rows and the columns on the outside. Those are not matrix entries. The vertex set is 1, 2, 3. So that's how we label the rows and the columns. And I look at it, and on the diagonal, I put for vertex 1 what its valence is. There's 3 edges coming out, so that gets a 3. And then for vertex 2, I see 2 edges coming out, so that entry is a 2 on the diagonal. And for vertex 3, I see 3 edges coming out. So that one gets that diagonal entry is a 3. And then on the off diagonal, like the 1, 2 entry, I just put minus the number of edges from 1 to 2. So that looks like a minus 1, which is also the number of edges from 2 to 1. It's a symmetric matrix. There's also a minus 1 in the 2, 1 entry. And then the 1, 3 entry is going to be a minus 2, because I see a couple of edges from 1 to 3. And the 3, 1 entry is also a negative 2. And the 2, 3 entry is going to be a negative 1.
Wait, did we, if the loop were there, would it be 4 for the middle slot instead of 2?
Great question. So why was I being careful about this and saying remove them? You don't want to let the loops count for any valence. So that's why it's probably better to remove them. Yeah.
Does it break stuff if the loops are still in there, or does it just?
It'll break stuff if you change the valence there. Yeah.
Okay.
Yeah, you got to get the valence right without the loops. Okay. So why did I introduce this thing? Here's the theorem, and this is a theorem from 1848. And those of you who've taken like a physics class where you do analysis of circuits and resistors and currents and Ohm's law and Kirchhoff's law, it's Kirchhoff. This came up in him analyzing electrical networks. Kirchhoff's 1848 matrix tree theorem is what it's called, because it counts trees and it involves matrices. So what it says is, if you take any vertex in the vertex set, you can use that to count the number of spanning trees. You take the determinant not of this full Laplacian matrix. It turns out that thing's going to have determinant 0. It's always a singular matrix, and we'll see why later. But if we cross out the VV row and column, so the row and the column indexed by V, that smaller matrix will be non-singular, and its determinant will be the number of spanning trees. It's kind of weird. So this is the determinant of what I'll call not L of G itself, but L of G reduced at vertex V. So let me just say what that thing is. Determinant of L of G with row V and column V removed. And that's what I mean by this thing called the reduced Laplacian matrix. Okay, that's crazy. Let's try this on the next page.
You say reduced at V or what?
Yeah, people talk about reducing it at V.
Okay.
In the electrical network theory, it actually corresponds to, if you've ever done this, where do you pick to ground the network? Where do you say the potential at a certain node or vertex is 0? I think of that's this choice, and that's where this matrix came up in Kirchhoff's work. The choice of V corresponds to the choice of the ground node. Okay, so we're going to do an example. Well, this matrix we were working with, the one that we just wrote down the Laplacian for. Yeah, so on the one hand, it should be, I don't know, we can reduce it in different places. Let's try reducing it vertex 1. We should get something correct. Let's also try it at vertex 2. Those two look like they should be a little bit different in terms of the calculation. Okay. So at vertex 1, let me just copy this matrix. We're going to essentially strike out a row and a column, so I may as well begin with it. Copy this thing. And maybe I'll just copy that whole bit. Copy. Except, let me do the striking out in red, right? Here I'm supposed to strike out column 1 and row 1. Here I'm supposed to strike out column 2 and row 2. And maybe I'll give myself a little more room. So this one up top is the determinant of a 2 by 2 matrix, right? It's indexed by the 2 and the 3 that are left. It's 2, 3 on the diagonal with -1s off the diagonal. So we get 2 times 3 minus -1 times -1. That's 6 minus 1 is 5, which is the number of spanning trees. And this calculation says it's also supposed to equal the determinant of this reduced matrix indexed by vertices 1 and 3. It has a 3 and a 3 on the diagonal, -2s off the diagonal. So we get 3 times 3 minus -2 times -2 is 9 minus 4 is 5, which worked. Did everybody see what Kirchhoff's theorem is saying?
Are you gonna do a proof, or are we just gonna?
I'm actually going to use it first. I want to show you a couple of ways in which it actually turns out to be rather handy and remarkable, and then we'll prove it. Yeah. So, other questions? Okay, so let's first of all say this is very useful in 2 different ways. Both, on the one hand, computationally. Because our deletion contraction method, if you analyze how many steps that takes to do your general calculation, using the deletion and the contraction, it takes about 2 to the number of edges in the graph. It's exponential in the number of edges. It's very bad, actually, computationally. But this is a determinant of a cardinality of V by cardinality of V matrix. Those you can actually do really fast. One can compute n by n determinants in not just like a polynomial in n, it's less than cubic in n. In less than or equal to a constant times n cubed. I forgot to say less than or equal to, at most. For some constant c. In fact, you can get it down to n to a power that's between 2 and 3. I think the best known exponent here for whether it's cubic versus quadratic, it's definitely slower than quadratic. People have provided lower bounds on the complexity of computing determinants, and you can't get it down to n constant times n squared, but you can definitely get it to better than n cubed. I can't remember whether, currently it's maybe like 2.4 or 2.3 is the best power or something that you can achieve there. So it's for some constant C. And the way you do it is via Gaussian elimination, something that you've all seen. Like the idea is that the same steps that you do when you row reduce an n by, a system of n equations and n unknowns governed by a matrix A, you do things like adding multiples of one row to another one. That does not affect the determinant at all. You swap two rows. That does affect the determinant, but it's totally predictable. It just changes it by a minus sign. And then the other thing you do is you scale a row, perhaps dividing by one of the entries. When you scale a row by C, totally predictable. It changes the determinant by that same scalar C. And so you just keep track as you do the Gaussian elimination, and you take your n by n matrix A to an identity matrix whose determinant is 1. You just track the minus signs and the C's, the constants that show up. You get a very fast determinant computation algorithm. Let me write that down. All right, what the heck? I should be stealing this stuff, not the example. Let's see. Since determinant of A is unchanged by adding a multiple of a row to another, negated by swapping rows, and scaled by scaling a row. So you just track all those changes as you take A to the identity, and you get a determinant algorithm. It's fast. It's less than or equal to C times n cubed steps. Okay, so this is actually the fastest way to compute the number of spanning trees in a graph. You write down its Laplacian matrix, you do one of these fast determinant calculations, boom, you can do it for humongous graphs. You can actually calculate the number of spanning trees.
Like it's proven the fastest? Is it just the fastest known?
Oh, I'm not saying it's the fastest, but it is much, much better than our naive deletion contraction, which was 2 to the number of edges. It's provably better than that in general. Yeah, I don't know that there's actually complexity lower bounds on computing a number of spanning trees. I'd be surprised if there was a faster algorithm actually, but I don't know if I'm aware of any results that say that. So it's useful computationally, but it's also theoretically, and we're going to see an example of this, because there's sometimes where you have graphs that are highly structured. We've already seen some graphs that are highly structured, and where you can actually compute the determinant via eigenvalues. So we're going to do one of these theoretically, because some graphs or families of graphs have enough structure to compute this determinant of the reduced Laplacian via eigenvalues of the matrix. So in fact, I'm going to do that for you. Any questions before I do an example of this? And then we'll come back and prove Kirchhoff. I'm just trying to, whet your appetite. Is like, this Kirchhoff thing looks like a good thing to know. All right, let's do it. So example, let's give a second proof of the Cayley-Borchert theorem. I don't know why it is that I can't say Borchert-Cayley. I'm so used to calling it Cayley's theorem that I have trouble putting Borchert's name first. Okay, so remember what this said. Borchert-Cayley theorem, I'm just going to remind you of its statement. It's really about tau of Kn, right? We didn't phrase it that way before, but this should be the number of spanning trees on n vertices labeled 1 through n, right? The answer was n to the n minus 2. That was the theorem. But let's think about this. Why is this the same as tau of Kn? Well, if we had a complete graph, let's do n equals 5 here. So let's label the vertices 1, 1, 2, 3, 4, 5. When we pick one of these spanning trees, right? Maybe this edge and this edge and this edge and this edge. That's just an arbitrary tree on vertices 1 through 5. And it's, you know, one of these things that we were talking about counting. So first of all, does everybody agree that another way of saying the Borchert-Cayley theorem is that tau of the complete graph, Kn, is n to the n minus 2? Okay. Good. So we want to show I need to practice my lassoing here. Let me take away the words this way. So first of all, let's compute Laplacian matrix for Kn. That's easy enough. Here we've got an example of n equals 5, right? Laplacian of K5. Right? This was a picture of K5. Well, it's going to have 1, 2, 3, 4, 5, indexing the columns. Columns and rows. 1, 2, 3, 4, 5. Every vertex has degree 4, n minus 1 in general. 4, 4, 4, 4, 4. And between any pair of edges, doesn't matter which I and j, if I and j are not equal, there's one edge between them, so we get minus ones. Minus 1, 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 minus, sorry. There's a lot of minus ones to say here. Oh my gosh, I'm probably drawing this badly, but I don't know. Minus ones on the off diagonal. Okay, so let's just draw the general picture. I'll try to be a little more neat when I do this one. It's got rows and columns indexed by 1 through n. We've got n minus 1s down the diagonal because every vertex is of degree n minus 1. It has n minus 1 neighbors, everybody but itself. And then off diagonal, we've got minus 1s. Agreed? And so let's figure out what the reduced Laplacian is. And as you can see, it doesn't really matter which row and column I choose to reduce on. They all look the same. So no matter how I pick the V, it's going to look like this. You're going to have n minus 1s on the diagonal. You're going to have minus 1s off the diagonal. And now it's going to be n minus 1 by n minus 1 squared because we removed one of the rows in the columns. It used to be an n by n, now it's one small. Okay? And this is the thing that I'm going to compute the eigenvalues and eigenvectors for, is this reduced Laplacian for matrix. So in fact, that's how I'm going to get at its eigenvalues. I'm going to show you its eigenspaces, all of them, and compute the eigenvalues and their multiplicities. That's how we'll get at the determinant. Everybody okay? All right. So for the sake of doing that, let me rewrite this as n times the identity matrix. This is like n down the diagonal with zeros, minus a matrix that's just a whole bunch of ones. Ones, ones, ones everywhere. So this is n times the identity matrix of size n minus 1. And this is jn minus 1, the all ones matrix of size n minus 1 by n minus 1. Everybody believe that? So here's the thing. We're saying then that Kirchhoff tells us that tau of kn, this thing we're interested in, the number of spanning trees, it should be the determinant of this n times the identity minus this all ones matrix of the same size. And now I'm just going to show you some eigenvalues and eigenvectors, enough of them that you'll believe it. So I'm going to show you a whole bunch of eigenvectors that have eigenvalue n. All right, let me carry this over. And just remind you what this jn minus 1 is on this page. It's all ones. And it's of size n minus 1 by n minus 1. So we claim that these vectors, v1, v2, up through vn minus 2 that look like this. 1, negative 1, 0, 0, 0, 0. 0, 1, negative 1, 0, 0, 0, 0. 0, 0, 0, 0, 0, 1, negative 1. All these vectors, they're all of length n minus 1 so that they could be hit by these matrices. These things are all eigenvectors. There's n minus 1 of them, linearly independent eigenvectors for this matrix with eigenvalue n. Why is that? Since these vectors, their coordinates sum to 0, that means when you multiply them by jn minus 1, it just annihilates them. Sorry, I should say they all just get sent to the 0. 0, 0, 0. Every row of jn minus 1 is perpendicular to these vectors. So when you do the multiplication, jn minus 1 times these things, you get a 0 row by row. But the n times n minus 1, excuse me, n times the identity, that of course just scales them by n. So when you take one of these vectors and do this computation, you get n times vi minus 0 times vi. It's just n times vi. They each have the eigenvalue n. And you can check they're linearly independent. You know, it's not too hard to, whoops, you know, do some row reduction. You can see there's sort of a triangularity going on there. They are linearly independent. I'll let you verify that yourself, that there's that many of them. Okay, so there's n minus 2 of these, and this is an n minus 1 by n minus 1 matrix. If I could come up with one more eigenvector with some eigenvalue that I claim is not going to be n, that's going to be linearly independent, and that's going to give us a complete system of eigenvectors and the eigenvalues. We'll know what all the eigenvalues are. We also claim, here's another one, that the all ones vector, 1, 1, 1, 1, 1, let me call that V0, is an eigenvector for this guy with eigenvalue 1. And why is that? It's because this all ones vector, it also, when you hit it with each of the rows of your matrix that's jn minus 1, you get the same thing every time. You get n minus 1 every time. N minus 1, n minus 1, n minus 1, which is n minus 1 times v naught. And so that means that n times the identity minus jn minus 1, when you apply it to v naught, you get n times v naught minus n minus 1 times v naught. There's just 1 times v naught. That vector is an eigenvector with eigenvalue 1. So this matrix has eigenvalue list. Well, it's got the eigenvalue n several times. It's got it n minus 2 times. N, for a total of n minus 2 times. And then it's got the eigenvalue 1 occurring once. And so its determinant is the product of those eigenvalues with the multiplicities. That's the Borchard-Cayley theorem. Right, it came from these n's. Believe it? This is one of these ones where you may want to go back to your linear algebra book if you kept it, or if you just don't have it all memorized anyway. Now, linear algebra is important, so it's always fun to have a class where you get to go back and think about how eigenvalues and eigenvectors work. But yeah, that's the fact. When you have a square matrix, if you can come up with as many linearly independent eigenvectors as the size of the matrix, that means that you can diagonalize the matrix and the eigenvalues will be down the diagonal. So they will compute the determinant for you. I'll let you ponder that a bit. Maybe ask me questions on Wednesday's class if this seemed a little weird, but this is just one instance where people have been able to compute for a family of graphs the number of spanning trees without having to do any counting at all, just by playing with eigenvalues, eigenvectors, and using the structure of the Laplacian matrix. Okay, so I'm going to turn off the recording in a sec. Any questions that people want on the recording before I turn it off? All right.